Hi everyone, welcome to electronics, introduction to electronics. I'll start by recapping some hopefully maybe familiar in the back of your minds GCSE physics. So you probably remember what a circuit looks like. It's like you have a battery, some wires, and then there's stuff connected to them. I'll first explain what happens in a length of wire. So you have two like preset things that you know about a circuit. You have voltage and resistance. So you can use the water analogy. Say voltage is like water pressure. You have like a reservoir, and then you have a pipe. The voltage is the water pressure in here, and then the resistance is like the diameter of this pipe, because how big the pipe is restricts how much current you can get through it. So there's this magical thing called Ohm's law, which is voltage over resistance equals current, which we write as I unintuitively, because C is for charge, and that's something else complicated that we don't have to worry about because that's physics. So, what next? Let's draw a simple circuit. We have a battery. Well, that's just one cell. If you link multiple of them together, that's a battery. And there's a positive end and a negative end. So you can think of the positive end as like the source, like your reservoir. 5-volt battery. Then we have a wire connecting the two ends. That's called short circuiting. You wouldn't have a circuit that looks like that because it would get really hot really quickly and probably break. But for the sake of explaining, when you connect this circuit together, you have 5 volts at this end, and this end is what you might refer to as ground. So you'll see it written, it's GND, or you could say it's 0 volts here. And when you connect these two ends, then you create a difference of 5 volts to 0 volts. So that's like saying there is 5 volts flowing through this. And okay, let's look at using breadboards, using this knowledge that we've just looked at. Okay, so we'll be looking at Tinkercad right now. The circuit mode, which lets you build various circuits and even play with block programming with microbits and Arduinos. And let's look at what a breadboard is. So when you're making anything, like when you want to prototype building a circuit, you'll be using a breadboard because it's got these holes in. You can just put like these jumper cables that have little like pins on the ends of them, and it just makes it really easy to like put cables in, take cables out. You can change things around, and when you've finalized your design, you can like turn it into an actual circuit. So these are for prototyping. So you can try things, move things around, etc. And if we look at it closely, it's symmetrical about this middle bit, and there's these two rails at the top and the bottom. So you can think of these as there being like one wire just going across this entire length here. And there's also one wire not connected to that one that's going across this entire length here. And it's the same on the bottom rails. And then these middle ones, the wires go vertically instead. So all of these like vertical lines are connected. But they don't connect with these bottom like ones. So that's half. Then there's a break here, and that's another half. And you'll see why that's useful in a second. So the plus and the minus don't really mean anything. It's just like you don't have to follow them, but it's useful if you use the labels, right? So usually you put a wire into the positive side from your 5 volts, like the positive end of the battery, and then you'll connect a wire. Actually, let's show you. So we have a very big battery, and the red here is positive, so we'll connect it here, and then say we put an LED in here. So we have 2 vertical wires here. These aren't connected, but we can connect the positive like rail to the I hope, yeah, that's the anode. So the like the positive leg of the LED. LED stands for light emitting diode. So it emits light, that's like the obvious part, but diode means it's one way. So if you connect it backwards, it won't do anything because physics. So I think this is the right way. If it's not, we'll just swap it around. But you want to connect the positive to the positive leg. You can kind of just follow the wire. So like you have a plus here, you're connecting this to this leg because this wire goes along this entire vertical line. Then we can connect another wire. We could like turn this into the ground rail, or we can use this one. Let's just use that one. And then we can connect the negative to the negative. And we start. And it works, but only for a millisecond because the LED explodes. So what's happened here is we have a current that is way too high for the LED to handle. So it gets really, really hot and it just burns out, like it melts inside. So you might remember from earlier, we define current by voltage and resistance. So we can't really, well, say we need to use 9 volts. Maybe we need 9 volts in other places, but in this like specific part of the circuit, the current is too high. So what we can change is the resistance. So you can imagine this as adding like a narrower pipe. Like say you cut your main pipe in half, and then you put like a smaller pipe that connects them. It's like a bottleneck which prevents too much current from flowing through this circuit. and then the current will be at a safe enough level for the LED. So it says here, we get a useful description. It tells us the current is 915 milliamps, and the absolute maximum should be 20. That's a pretty big difference. Usually you want about 15 milliamps. Whenever you buy like a component, it will tell you on the data sheet how much current is safe to put through it. So say you buy some LEDs, it will say like, these are rated for 15 milliamps. So that's what you want to aim for. So we know what we want, and we know what voltage we have. So that's two things we can't change now. We know what current we want, that's fixed. We know what voltage we have, that's fixed. So we want to find the variable resistance. So going back to Ohm's law, we have it right here. We can rearrange that to R equals V over I. So we have 9 volts over, and we want 15 milliamps, but we need to convert that into amps because the unit ohms is, like 1 ohm is 1 volt over 1 amp. So 0.015. Now, if I put that into a calculator, we get 600 ohms. So that tells us we need a resistor that has the resistance of 600 ohms. There are sheets, like there are like cheat sheets that tell you how to tell the value of a resistance from its color bands, but that's like, you never need to memorize that because there's websites that just do it for you. But here we can just set the value to 600 ohms. So that's our resistor. And we can put the resistor anywhere in the circuit, because if you think of it as a loop, it's a closed loop. So the current has to flow all the way around it. So no matter where the smaller pipe like section goes, it will always restrict the current in the whole circuit. So say we want to put it like here, we can actually, yeah, just do it that way. Okay, I'm gonna move this down, and maybe, yeah, there we go. So now this resistor is like turning these 2 lengths of wire into just like one section of the circuit. So it's like bridging the gap. And then we can connect this bit instead to the negative side. So you can follow the wires again. We go from the positive along here into the positive side of the LED, goes inside through the LED, down into this leg, goes across here to the negative rail, and back to the negative side of the battery. And we start it, and it doesn't explode this time. So that's how you use Ohm's law to not destroy your circuits. Now we'll look at microcontrollers. So the easiest one to learn is the Raspberry Pi Pico. They're also extremely cheap. You can get one of these for like £4-5. So really nice. And we want to look at these little metal bits on the edge, along the edge. Okay, there we go. These little copper things are called pins. So these are your inputs and outputs, you can call them. And the way you use them is, this is like a computer, right? So it computes things, and you can connect wires to these to send electrical signals, and then the computer can then read these signals. So you can think of a signal as, an electrical signal can look like a digital signal, which is either 0 or 1, and that might look like this, in which case a 0 is defined as there being 0 volts, and a 1 is defined as there being, say, 5 volts. So you can create logic that changes the voltage that's being put into the pins, and then the computer can read whether that's like this, like a 0, or a high voltage, which could be interpreted as a 1. There are also analog signals, so these could be like smooth, and it's the same principle, where it could be from 0 to, say, maybe 3.3 this time. So it's between a low and a high voltage, and it could change continuously instead of discretely. Like discrete meaning there's fixed like steps, and continuous being it's constantly changing. So we're going to write a very simple program. Okay. So we're looking at Walkway right now, walkway.com, and the benefit of that over Tinkercad is that we can program using actual text programming languages instead of blocks. So it's more realistic. Like, you can design a circuit in this and then build it in real life. The only downside of this is that it will not check like current through components. So say we built the original circuit here without the resistor, it wouldn't tell us that there's anything wrong with it. So this is more about designing digital circuits rather than analog circuits, although it still provides some analog like features, but we'll look at that later. So this is the default program. If we run it, it just prints to the console, hello PyPico. This is standard Python code that you would have seen before, and specifically this uses like a version of Python called MicroPython. It's pretty much the same, but it's just stripped down. It's like a bunch of the like standard libraries are removed from it because you don't really use them that much, and it saves space. Okay, so let's give an example. Wiring an LED. I already forgot which side. I think, yeah, anode is positive. Okay, so Walkway really conveniently labels all of the pins, so you don't have to Google Pico data sheet. if you're working with a physical one, you'll want to get one of these images up to reference. And these tell you what all of the pins are used for. So you can see some of these are ground pins. So that's like your negative terminal. Essentially, all of these ground pins connect to the negative side of the battery, say, or the power supply. So whenever you want to close your circuit off, you want to connect to ground so that it's a complete, like, closed circuit. What else is interesting here? We have 3.3 volts out here. So this is like your positive terminal on the battery. So you could just use this, the Pico, as a battery, really. You could connect, I'll show you right now. We can connect the positive of the LED to 3.3 volts and the negative to just any ground pin. We run it, the LED lights up, because this is just constant 3.3 volts out, goes through, and it goes to the negative terminal, to ground. But say you want to control this using, say you want to program your LED, then we can also output 3.3 volts from any of these digital pins. Oh. So I'm pretty sure any GPIO pin is, any GPIO pin can be used as a digital pin. That meaning it can output a high or a low voltage. So 3.3 volts or 0 volts. There's also these few analog pins, which we might look at later. So instead of using 3.3 volts, the constant 3.3 volts here, let's use the GPIO pin 0 and connect that to the anode. So now we can program this to output 3.3 volts here, or to output 0 volts here, and then connect this to any ground pin again, say that one this time, and we can now program, say LED equals, and I think we need to import pin from machine, import pin, then we use pin 0, and 0 is just the ID of the pin, so these are labeled. That's 0, 1, 2, 3, 4, 27, and we want to write pin dot out. Then we can do while true, for example, just an infinite loop. Let's have it wait like half a second between each loop, and then do LED.toggle. And that should, make it flash. So let's go through this again. We're importing the class pin to create a pin object with ID 0, and we're defining it as an output. So we write pin.out, which tells this pin object that treat this as an output, not an input, because any pin, any GPIO pin can be input or output, hence IO meaning input/output. And then the main program is just forever wait half a second and toggle it between high and low. So we have a simple blinking LED. let's look at inputs now. So say you want a button. Actually, there's two types of buttons. Oh, that's just a small one. That's not helpful up here. Okay, but the way these buttons are wired internally, because you can see they've got 4 legs, or like 4 pins. It's a bit confusing, but you can just think of this as these, like the straight, the ones that are straight across from each other. Like these are, how do I put this? I guess you can see that this is like a continuous kind of line here that these two create. So these two are connected, and these two are connected. But these two sides, like the top 2 and the bottom 2, are not connected. So you don't actually need to use these two, because these are connected to these two. So we can have, say, let's use this GPIO pin. And it doesn't matter, like, if we connect it, like, which way round we do it, because the button's symmetrical. So we can, like, unlike a diode, which we can only send current through it one way, we can send current any way through a button. Oh, and when you press the button down, it connects these two, like, sides, which I didn't mention earlier. So, yeah, so we want to connect a GPIO pin to one side, and we want to connect the other side to ground. And this will be a little unintuitive, but I'll try and explain it after. So we have this wired up, and we have GPIO pin 26. So let's define another pin of 26, and this one's called pin dot in, to say that it's an input. And yeah, let's do print button dot value. I think that might be wrong, but no, it's correct. So when you have, like, just an exposed wire that's not really, like, connected in a circuit at all, there is electricity going through it, very, very little, but there is some that's caused by the electromagnetic waves all around us from, like, the devices, like screens, or like radio towers, and just everything. So we call that state floating, where it's not 0 and it's not 1. Like, it's not low or high. It could be anything, and you can't really tell what value it is. So you can look at this and think, well, this pin is connected to here, but it's not connected to anything else, because it's not connected to this side. So you can kind of think of this pin as not being connected to anything. So it's working as an antenna right now. It's just receiving random noise that we don't care about. So if you read just a random pin in real life, the simulator doesn't show it. But if you do this experiment yourself, and you do, like, print button.value, or like pin.value, it will just give you random values. It will change. It'll be 0, sometimes it'll be 1. You can't rely on it. So internally, when this circuit is just, like, exposed like this, we want to, well, we call it grounding, right? We want to connect it to ground, which tells it, well, we can do it both ways. We can either connect it to ground, or we can connect it to a high voltage. So that like puts it, depending on which way you do it. Say we connect it to a high voltage, then that fixes it at a high voltage. It's no longer floating. So it's like, it's defined now what value it has. And the Raspberry Pi Pico has this functionality like in its internal circuitry, which you can just use by adding a little bit of code. You can, I guess, for the sake of understanding it better, and I did this myself, I recommend that you read about pull up and pull down resistors, and you try and create one yourself. Like, you try and ground it yourself, and it's really simple to do, but it's a little unintuitive. So we do that with pin dot, I think, no, I'm going to Google this because I'm going to get it wrong. Micro Python pull up. So these are the docs for MicroPython. And we have, okay, it is just that. So we want to add a third argument, which is pin.pullup. Pin.pull up. Now we run it. Okay, and now it's reading ones all the time. And if I press the button, that I don't think, actually no, that will, okay, ignore that. But for now, it's gonna show us ones because we've connected this loose, like not connected to anything pin to 5 volts, 3.3 volts, I mean. So a high voltage. So it's showing ones now instead of, well, it would be showing zeros sometimes, ones sometimes. And now, when I press this button, when I hold it down, it doesn't do anything. Okay. I may have done this the wrong way around. Ah, okay. Let's connect this to that. Yeah, this is GPIO. Let me try this again. Okay, maybe I connected to one of these by accident, but it works now, so I don't know what changed. Maybe it's because I clicked restart here instead of actually stopping it and playing it again. But okay, it works now. When I press the button, it goes 0 now. When I don't press it, it goes 1. And to explain what's happening when I press it, the circuit becomes closed. So say there's like, I'm going to draw this, it'll be easier. Okay, let's look at say we have our 5 volts here, or 3.3 volts here, and this is the Pico, and this is the pin. But imagine that this is like this 3.3 volts is coming from, it's like somewhere in the internal circuitry of the Pico. In fact, I'll draw it that way because I can. So we have like 3.3 volt source somewhere inside, and it connects to the pin, and the pin is like read by some random circuitry inside, so we don't worry about that. And then outside, the pin is connected to a switch. Have I done this right? I think so. And the switch connects to ground. So we have G and D here. So that's the circuit. I want to draw this above for clarity. Okay. So you can kind of think as in this mode, actually always pretty much, you can think of as a pin internally ends up connecting to ground somewhere. So like there's some circuitry that connects that to ground, and there's like some resistance along that circuit, and you'll see why that matters later. So I think we need a resistor as well. So a rectangle in a circuit is just a resistor. I think that's right. Yeah, so when the switch is disconnected, this is a circuit along, I'll use a different color. This is a circuit, like a closed circuit, because you have 3.3 volts going to ground through the pin. So the pin is reading high. When you close the circuit here, then there's less resistance along this path than there is along this path. Yeah. So the 3.3 volts goes this way instead. So it still goes to ground, but it doesn't go through the pin. So the pin reads 0, and that's pretty much what causes it to behave that way. We don't hold the button, it's 1. We hold the button, it's 0. And let's mess around with this. Let's make the LED turn on only when the button's held down. So let's do like if button.value equals, so when it's held down, in this case, it's a 0. You can make it work the other way around, but it's slightly different. And we want, we don't want to toggle this, we want to set it to a value, and I don't remember how to do that. So let's see the docs again. Okay, it's just pin.on and pin.off. So you can see here pin.on sets the pin to output 1, pin.off sets the pin to output 0. So we'll do pin.on, and if it's not held down, we want to do led.off. And we don't need to to wait each time, because we want to be constantly reading the input instead of waiting half a second between reading the input each time. We stop this and start. The LED is now controlled using the button. Okay, we'll look at analog inputs. So let's leave that circuit as is, but let's get a slide potentiometer. Potentiometer is another word for variable resistor, which means a resistor that changes its value. So it's not just like what we saw here. This resistor can never change its value, but a variable resistor can. So this slider is like, when it's all the way to the left, there's maximum resistance. When it's all the way to the right, there's no resistance. So it's like, when it's all the way to the left, it's not letting any current through. When it's all the way to the right, it's letting all the current through. And you can measure this using the pico. Or you can use it to control like an LED directly, for example. But we can't do that in this simulator because it's more about digital electronics. So let's start. So we want to connect this to a high voltage, because it's going to transform that voltage to a lower voltage depending on how much resistance there is. Yeah, and we want to connect this to ground. And the reason for that I might cover afterwards, but it's quite physicsy. So let's just look at applying this for now. And then we want to read the signal. So that is going to be a voltage like level between 0 and 3.3, including those values. And we can just read that like and use it as like a ratio of, like, we can interpolate between these two ends basically. When we click on this, it already highlights which of the pins are analog pins. So the pico only has these pins as analog pins. And some microcontrollers don't have analog pins at all. So you'll need an analog to digital converter, which is just another circuit that will convert it. It'll be like a little teeny square, and you like connect one end into it and the other end's digital magically. So like this outputs like a continuous, actually we can go back to the diagram. The slider creates a signal that looks like this, where it's like you put the slider like all the way, then you get up here, say you slide the slider a bit, and then it goes down. And yeah, and the analog to digital converter converts this like signal into a digital number basically. So in this case, you'll see in a moment, it gets converted into an unsigned integer, so a positive integer of 16 bits, which is between like any integer between 0 and like 65,000 something. So the analog digital converter in the Raspberry Pi will receive this wave, like this analog input. When it reads like 0, that's a 0. When it reads 3.3 volts, that will be 2 to the power of 16 minus 1, because that's the maximum like unsigned integer of 16 bits, like that you can store. Basically the biggest number you can store in 2 bytes of data, and you'll see that in a second. So it's not like turning it into another signal, it's turning it into just a variable, like a piece of data. Or I guess you could encode like the number as a signal. Like you can send binary across a wire by saying like low is 0, high is 1. But I'm pretty sure one of these. Okay, say we look at this one. Okay, I2C. So that's like a protocol for like reading, for sending data serially. So serial just means you're sending data over time. Like by like you're sending a sequence of bits, you're sending a sequence of zeros and ones to interpret as a message, right? So these pins at the top, like the A's, are I think those are your analog inputs. So these are like your analog pins up here. And the circuitry in the converter, I guess maybe it's confusing to call it a converter, because it's not really converting one signal into another. But hopefully you'll see when I... Yeah, so the pins receive the analog signal. The circuitry in the converter reads the signal and stores it in its like memory. And then the I2C protocol lets, like, for example, your Raspberry Pi to read those variables from the memory. So I hope that makes sense. Yeah. Okay. Yeah. And the Raspberry Pi has that built in, that circuit. So we just need to program this now because that's connected. So we've got 3.3 volts in, we've got ground out, and then we have this signal going into a GPIO pin, which is 28, I believe. So let's get slider equals pin. It's 28, right? Yeah. Pin dot in. Actually, no, that's wrong. We want to import ADC, which is analog to digital converter, and just do that, don't we? Yeah. I think that's right. If it doesn't run, we'll fix it. I guess let's just print slider dot read U16. Yeah, okay, we got somewhere. So slider on the left, it's reading zeros. Slider in the middle, it's reading 32,000, which is half of the maximum. Slider all the way to the right is the maximum 2-byte unsigned integer. So 2 to the power of 16 minus 1. And I guess let's just print this. Let's like say we want to know the voltage. Like we want to interpret this as voltage instead. we can like do some arithmetic on the value. So divide it by that maximum value and multiply it by 3.3. So we're kind of just mapping it from between 0 to 65535 to instead be between 0 and 3.3. And now it's like that's 0 volts, that's 3.3 volts, that's like 1.6 volts. So there you have it. You can make pretty much like any basic game controller using these like parts. So that's all I've got. Hope you enjoyed.